for this screencast, we're actually going to do a two-dimensional aerodynamics problem. So one of my students sent me this problem a while ago, and I'm just getting around to film it. And so the idea is you have a cylinder with a certain radius, big R, and you have some flow going across the cylinder. Now, one thing that they don't really, at least when I was an undergraduate, that they don't really mention about flow going over a cylinder is that in order for this cylinder to generate lift, you actually have to have the cylinder rotate. And that rotation is basically the Magnus effect. I'm sure there's millions of YouTube videos out there on the Magnus effect. But the idea is that if the cylinder is rotating this way, actually you want it to rotate the other way, sorry. So if the cylinder is rotating that way, the skin friction on the cylinder itself will cause the flow to accelerate up here. So V will be greater than V infinity, right? V infinity is out here, that's the free stream airspeed. And so the flow will be faster up here and it will be slower down here, so V is less than V infinity. And what that will cause is your coefficient of pressure will be high down here and your coefficient of pressure will be low up here, and that will generate some lift. And so what two-dimensional aerodynamicists try to do is basically call this spinning effect circulation, and that's denoted by gamma, okay? And so you'll see in this stream function, so I'm going to write, sorry, this is circulation, okay? And circulation really, it's hard to sort of quantify that. Like if you say you have like a milliliter of water or like, you know, a pound of snacks or something like that, like that's something tangible that you can kind of hold on to. But circulation is really more of just like a two-dimensional aerodynamic parameter that you kind of have to just say, well, if it's bigger, there's more circulation, and if it's smaller, there's less of it, okay? So in this case, we're just going to say that the streamline function has a V infinity flow that goes over it, and it has some circulation. How much? Well, that just kind of depends on, you know, how fast the cylinder is rotating as well as the skin friction on it, okay? So we're going to write the stream function of a cylinder, a flow going over a cylinder while it's rotating. And again, this is just from a two-dimensional aerodynamics textbook as V infinity R. R, I'll tell you the units in a second. Sine of theta 1 minus big R squared over little r squared plus gamma, and there's that circulation term, over 2 pi natural log of little r over big R, like that. Okay, so that's a really, really long analytical expression that describes this two-dimensional flow. And again, don't get caught up in the math. You're literally blowing wind at a spinning cylinder. Spinning cylinder. So you have a spinning cylinder and flow is going over it, okay? So what do all these terms mean? Well, the idea is that this stream function is in polar coordinates, okay? So rather than using x and y, right, so if you draw like a Cartesian coordinate frame like this, x and y, where you have x going this way and y going that way, we're writing it in polar coordinates where you have r is the distance from the origin, and then theta is that angle. And so typically we define the origin point as right in the middle of the cylinder. And so when r equals r, right, so when little r equals big R, this is the surface of the cylinder. And that's going to matter later on as we determine lift. Oh yeah, I didn't tell you what we're doing. We are going to compute lift per unit span, okay? This is our question mark for today. We're going to try and find lift per unit span. It's probably going to take this, I'm using my tiny whiteboard just because of the way my office is set up, so it's probably going to take a couple boards to get through this, but yeah, you're watching a YouTube video, so you can pause it and follow along. I'm going to try to show my steps as much as I can as if I was giving a lecture here, so let's get it. Okay, so the first step is to find the velocity of the flow. So this is a stream function. We need to convert this to velocity. This is the velocity in the radial direction. This is equal to 1 divided by r, partial derivative of the stream function with respect to theta, and then the velocity in the theta direction is equal to negative partial of psi with respect to r. And now if you write the vector field, v with an arrow on it, the vector field, you're going to get that it's vr er hat plus v theta e theta hat. And so, you know, again, in Cartesian coordinates you would have an x direction and a y direction. In polar coordinates you have a radial direction and a theta direction. And so that's what these units are here. Okay, so we are going to take these partial derivatives here, and we are going to do the partial of psi with respect to theta first. And so we take a look at this. There's this term, which is not a function of theta, that's not a function of theta, and that's not a function of theta. So that whole term pops out, and you just get the whole thing times cosine of theta. This whole term over here is also not a function of theta, so that just goes away. Okay? I don't know if you know how to do partial derivatives. I'm assuming if you're watching this video you do. I think Aerodynamics, the prereqs, have Calc 3 in it, or Calc 2. Do you do partial derivatives in Calc 1? I'm assuming you have Calc 1, 2, and 3 under your belt. If you don't, then you would need to go review your notes. Anyway, so you're just going to get v infinity r cos theta, and then 1 minus r squared over r squared. Okay? And that right there, boom, we're going to put a box around it, is the partial derivative with respect to theta. Now, the velocity is 1 divided by r, so after I erase the board and write the velocity field on there, remember that that r is going to cancel. So if you're following along and trying to do this by hand, just keep in mind that that r is going to cancel when we get that vr there. Okay. V theta is a little bit more complicated, and the reason why is because, V theta is more complicated because you have to take a derivative with respect to r, and unfortunately here you have to do a product rule, and here you have to do a logarithm rule, and so things just get kind of, I want to say kind of nasty. Okay, so let's take a look at this term here first. So you basically have a term here and a term here, and so we're going to do product rule on that. And so product rule says you take a derivative of this guy first times this guy, and then you add this guy times the derivative of this guy. Okay, so let's write that down. You're going to get del psi del r. Okay, and remember there's a negative sign here. We'll deal with the negative sign later. We're going to take a derivative of the first. The partial derivative of r with respect to r is just 1. So you're going to get v infinity sine theta, and then we're just going to multiply by that second term. Okay? Then we have to add the first term, so we're just going to throw a v infinity r sine theta, and then now we have to take a derivative of the second term. Well, the second term has two terms. The derivative of 1 with respect to r is 0. It's a constant, so it just goes away. This minus sign is going to pop out, so I'm going to pull this minus sign out. And then you're going to get this partial derivative of r squared. Now, whenever you take a derivative, you bring down the negative 2, so you're going to get a negative 2, the r squared stays there, and then you're going to get an r cubed. Okay? And so this negative is going to cancel, okay? And then this r cubed is going to cancel with that r, and so you're just going to get an r squared there. Now, we'll worry about all that simplification later. Let's take a look at this natural log here. Now, the natural log of r over big R, you have to do a expansion. This is equal to the natural log of r minus the natural log of big R. And so you'll see if I take a partial derivative of this term, it's the same as taking a partial derivative of this term minus this term. Well, this term does not have an r in it, which means that that just goes away. So if I take this as a constant and just pull this out and write gamma over 2 pi, and then take a partial derivative of this, I'm just going to get the partial derivative of natural log of r, which is 1 divided by r, and that's it. Okay? So now let's collect all these terms here and see what we get. Well, remember how I was saying that this r is going to cancel with this guy, and we're going to get an r squared here. This plus is going to cancel with that term. And then you'll notice that you have a v sine theta r squared over r squared minus, but then you have a v sine theta 2 r squared over r squared. And so those will actually add together, and you'll get that del psi del r is v sine theta, and then you're still going to get that 1, but you're going to get plus. You're going to get a minus 1 plus a 2, so you're going to get a plus 1 r squared over little r squared, and then plus this gamma over 2 pi r. Okay? Whoop. And there we go. If you're following along, see if you pause the video and see if you got those two partial derivatives. Again, we're going to take this term and divide by r. That r is going to cancel. We're going to take this term, plug it in here, and put a minus sign in front of it, and that is going to give us the velocity field of the potential. So again, pause the video, see if you got the same thing. I'm going to pause the video as well, erase the board, and come back. All right? Okay, folks, we're back. So hopefully you got this. This is the velocity field over the cylinder. And so again, remember I had to divide by r to get that r to go away, and then I had to put a minus sign in front of the v theta. Now, In order to compute lift, we need to get the coefficient of pressure around the entire cylinder. Now that's at the surface. If you look at 2D lifting line theory and things like that, you're looking at the coefficient of pressure at the surface of the body, and that is what is actually transferring the momentum, the force, the pressure force that's applied to the cylinder. That is what you're trying to get. And so I was saying earlier that at the surface, I think I said this in the previous board here, little r is equal to big R. So at surface, okay, little r is equal to big R. So what you'll notice is that if I plug in big R into little r, I'll get big R squared over big R squared, which is 1. 1 minus 1 is 0. So at the surface, the radial component of the velocity is 0, which makes sense, right? If you look at the cylinder, if you had a radial component of velocity, you would have flow going through the body of the cylinder, which doesn't make any sense. You can't have molecules go through a solid body. So that means the radial component is just completely 0. The only component that exists is the tangential or the theta component, okay? And so let's look at the theta component. So if I plug in big R over here, I'll just get a big R. If I plug in a big R over here, I'll get 1 plus 1, which is 2. So my radial component of velocity is just negative 2 v infinity sine theta minus gamma over 2 pi r, all right? And there is our tangential velocity. Now what's interesting and kind of convenient about the tangential velocity is that I wrote the vector field in the previous board, and so that the vector field is Vr Er hat plus V theta E theta hat. Well, if the radial component is 0, it just means that the magnitude of velocity, so V, so if I just write the velocity field, V, the magnitude of it, it's just equal to V theta, which I already have over here on this board. So that means, I'm going to turn my page in my notes. I only have one more page of notes here if you're curious how long this is going to take. Then I can write the coefficient of pressure, and again, this is just an equation from a 2D aerodynamics book. And I think this is from Bernoulli. We're assuming in viscid, incompressible flow here is 1 minus V over V infinity squared. And so you can kind of understand how this works, right? If V is equal to V infinity, the coefficient of pressure is 0, right? So there's no coefficient of pressure there. If V is larger than V infinity, so the flow is faster, I get a negative coefficient of pressure. If V is lower than that, then the coefficient of pressure would then be bigger than 0, if that makes sense. And so a high pressure, low speed will have a positive coefficient of pressure, and then a low speed, high pressure will have a negative coefficient of pressure. I feel like I didn't say that right. Okay, so if velocity is greater than V infinity, so you have a high flow speed, then you will have a negative coefficient of pressure. If your velocity is less than V infinity, so that's a slow speed, you will have a high coefficient of pressure. Okay, I think that makes sense. Okay, so this is where things get kind of nasty, because the problem is that I have to plug this into here and then square everything. Okay, so the first thing that we're going to do is we're going to write the coefficient of pressure is 1 minus, and the nice thing is that this first term, the V infinity, cancels, so I just get negative 2 sine theta, right, which is kind of convenient, and then I'm going to get minus gamma over, and then I'm just going to throw the V infinity in there, so I'm going to get 2 V infinity pi big R, and I'm sorry, I forgot to plug in big R over here. Okay, hopefully, maybe you guys caught that and you were freaking out. You were already posting in the comments. Dr. C, you did this wrong. Okay, if I had students watching me, they would have grabbed that. Okay, now we're going to square this. Okay, FOIL, right? First, outer, inner, last. Okay, so we're going to do CP equals 1 minus. So we're going to do the first term squared. So I'm going to get a 4 sine squared theta. Then I'm going to get the outer and inner is basically the same thing plus 2. So when I multiply these two together, the 2's are going to cancel, but then I'm going to add them together again. So I am going to get another 2. So and then the minuses cancel, so I get plus 2, and then just the whole thing multiplied by each other. So I'm going to get a gamma sine theta over V infinity pi r, and then finally the second term squared, so that's just going to be plus gamma squared 4 V infinity squared pi squared big R squared. And that is my coefficient of pressure right there. Boom, bada bing, bada boom, done. Okay? So this is going to be my second board. Again, I'm going to pause the video here. I think I'm also going to switch markers. So I will be back in the next one. I'm going to pause it. You pause it, follow along, see if you can get the exact same thing. And when I come back, we'll do the last part where we compute the coefficient of lift. All right, folks. So for the next part, I'm not going to rewrite the coefficient of pressure equation just yet because there's a couple things that we need to do to simplify. So remember, this is our cylinder. I switched to a red marker. I hope that's okay. Does that come out on the video all right? Yeah, that's coming out okay. All right, so what we need to do is we need to remember that our origin point is here. This is theta equals 0. Over here is theta equals pi, right? And so this is sort of a clockwise rotation, and then over here is, 0 and 2 pi, okay? And so we need to integrate, right, the coefficient of pressure across the upper surface, and we need to integrate the coefficient of pressure across the lower surface, okay? So the coefficient of lift is equal to basically the difference between the two. And so what we do is, and again, you have to look in your aerodynamics textbook to find this, but you're going to get 1/2 pi to 0. So this is from pi to 0. That's the upper surface. The coefficient of pressure on the upper surface, that's Cp comma u, coefficient of pressure upper surface, times the sine of theta d theta. And this sine theta d theta comes from converting to polar coordinates. So if you write the coefficient of lift in Cartesian coordinates, you won't have this sine theta d theta, but when you convert to polar coordinates, this pops up. And then you're going to get minus the integral of the coefficient of pressure on the lower surface. So you're going to get minus 1/2 again, and you're going to get pi to 2 pi of the coefficient of pressure on the lower surface, again, sine theta d theta. Now, there's a couple things to remember. First is that if you have an integral from a to b, f of x dx, that is equal to negative the integral from b to a, f of x dx. So if you notice, this goes from pi to 2 pi, and this goes from pi to 0. If I flop these integrands, so I'm just going to kind of do this on the fly. If I flip this to 0 and flip this to pi, I can throw a minus sign on there, and everything is completely preserved. Okay? So that's the first thing that I'm going to do. The second thing that I'm going to realize is that now I have sine theta d theta is the same, sine theta d theta is the same, the 1/2s are the same. The only thing that's different is the coefficient of pressure on the upper and lower surface. But if you remember from the previous board, the equation for the coefficient of pressure is only a function of theta, and it's a scalar equation. That is to say that the equation for the upper surface and the equation for the lower surface is the same. Now that doesn't mean that the pressure is the same. If I plug in theta, the limits of integration are going to be different for the two integrals. But I can actually go ahead and just erase the upper surface and the lower surface because those equations are exactly the same. Sometimes when you have a wedge, you have like a completely different equation on the top and a completely different equation on the bottom. But that's not the case for this cylinder. And so now that means that I can just completely combine this into one equation. And I'm going to go ahead and just, for the sake of not using another board, I'm going to combine this into one and say, hey, this is really the integral of minus 1/2 0 to 2 pi, right? I've combined the limits of integration, the coefficient of pressure sine theta d theta. And that really simplifies the math there because now I just have one equation that I need to deal with. Okay, so now I'm going to plug in that CP equation, and I'm going to get something really, really large here, right? And so I'm going to get the coefficient of lift is equal to minus 1/2, and I'm going to go ahead and leave that pulled out. And then I'm going to grab all of the different parts of the coefficient of pressure. So I'm going to get an integral from 0 to pi of 1 sine theta d theta. That's the first part of the equation. And then I'm going to get a minus, sorry, this is to 2 pi, integral from 0 to 2 pi of 4 sine squared theta. And then that's going to be multiplied by sine theta, so there's going to be a sine cubed d theta. And then minus the second term, you're going to get the integral from 0 to 2 pi of 2 gamma. There's a sine theta in that middle term, so you're going to get a sine squared theta over pi r v infinity d theta. And then finally that last term is the first outer inner last. That was the last term squared. You're going to get minus 0 to 2 pi of gamma squared over 4 pi squared r squared v infinity squared sine theta d theta. I'm running out of room here, and then you're going to get that massive bracket here on the end. I wrote a little bit too big here, I'm sorry. Okay, pause the video, see if you kind of follow this, and see if you can put that. Again, the coefficient of pressure equation I posted on a different board, and then I threw that into here, and so here are the 4 different terms. Remember, they're all multiplied by sine of theta. Now, there are a couple simplifications here. First of all, if you integrate sine theta from 0 to 2 pi, you get 0. If you plot sine of theta from 0 to 2 pi, there's a upwards hump, a downwards hump, and they cancel each other out. Sine cubed, because it's odd, and sine theta is also odd, this one is also 0. That one goes away. Sine squared theta, on the other hand, sine squared theta will be 2 humps, and you basically get the area of a unit circle. So the integral of sine squared theta d theta is actually pi, and the pi's will cancel. And so we'll get a CL minus 1/2. There's the bracket. We'll get a 0, a minus sign. So the minus is going to cancel. Throw a plus over there. And we're going to get 2 gamma pi. The pi's will cancel. And so I'll just get 2 gamma over r v infinity, like that. Okay? Then the term over here, all of this, gamma squared, 4 pi squared, r squared, v infinity, those are all constants. That pops out. You integrate sine of theta from 0 to 2 pi, that also goes to 0. It's wild how all of these terms go to 0, and you literally get this. So the 2's cancel, and you get to the coefficient of lift. I'm going to draw an arrow here. Is just gamma over r v infinity. Okay? And so the coefficient of lift then is really just a function of how big the cylinder is, how fast the flow is going, and then the circulation, which is again, how fast the thing is spinning. Now remember, I wanted to find the lift per unit span. So the lift per unit span is 1/2 rho infinity v infinity squared, the area of or actually this is 2-dimensional, so it's the mean aerodynamic chord of the cylinder. Well, not the mean aerodynamic chord, it's basically like the reference chord length. C times the coefficient of lift. And so the lift per unit span is 1/2, that's the density. That's not how you draw density. Density, rho infinity, v infinity squared. The characteristic chord length of a cylinder is just 2r. And then the coefficient of lift we just found is gamma over r v infinity. And so you'll get 1 v infinity will cancel. The 1/2 cancels with the 2. The r cancels with the r. And you actually get, and this is freaking wild, the lift per unit span is the density times the flow speed times the circulation. And so in viscid flow, incompressible, using 2D aerodynamics, the lift per unit span actually does not matter how big the cylinder is. All that matters is how fast the flow is moving and how much the thing is rotating. Now obviously in real life you get a ton of skin friction, and so that's not necessarily true for real life. But at least in 2 dimensions, you just get this simple equation here. And this is wild. If you remember the 3 boards ago with the stream function, that stream function was huge. It had like natural logarithms and squared terms and all this and sine thetas. And at the end of the day, you just get these 2 simple results right here. So if you're trying to solve for the 2D lift over a cylinder, you could go through all that math, or you could just use these simple shortcuts down here. And I hope you learned something. I hope I tried to give you some diagrams and graphics to kind of give you a more tangible way to hold on to this kind of thing. And if you want to do that fun experiment where you take a toilet paper roll or what are those things called? A paper towel roll, and put some end caps on it and spin it, you can kind of watch, basically in real life flow over a cylinder. And this is all the math that's behind it. So if you can follow along with this, you're one step closer to being an engineer. I hope you had a good one, and I'll see you in the next video.